Yeah, if you guys just received email from university, the storm advisory. So it says that starting at 2 p.m. today, so all the classes needs to be online. Probably started at the right time, so it's good that we move it online. Okay. Yeah, it's just for our safety, and then maybe there will be some arrangements for the Wednesday and Friday, Wednesday and the Thursday classes too. Yeah, you guys can read more about the emails later on. We'll see how things develop for Thursday. So basically, if you track the hurricane, it moved east and basically south a little bit. So we may get some impact. Okay. All right. So let's get started. In this class, we're just going to continue our discussion on the BOD, the biochemical oxygen demand. So I know that last class we had quite a lot of derivations there, and the BOD might be a new definition or new idea for you. So let's try to have some applications. So basically, this time we're going to apply the BOD into the study of the river water quality. Okay, so you guys can see my screen, right? So right now it's on the front page.
Yeah.
Okay, that's good. So the associated reading is chapter 9. And then if we do a quick recap, so last class we mainly discussed we started with the oxygen demand and dissolved oxygen. Okay, so that's OD and DO. So we said that for dissolved oxygen, there's a limit, right? So basically it's dependent on temperature, and normally we have a maximum DO under normal temperature to be, let's say 8 to 8.5 milligram per liter, okay, which is a very small amount. But for the oxygen demand, this is not constrained, okay? So we said that basically the oxygen demand is how much oxygen these organics are going to require to get a fully decomposition. Okay, so we give an example of if we have 1 liter bottle, right? And then just put in 1 gram, let's say this is 1 liter, and then put in 1 gram of sugar. Then if we further cap it, then the dissolved oxygen will just quickly go to 0, right? Let's say this is time and then DO, because even 1 gram of sugar in water is already a large amount of organics. Okay, so because of that, people want to determine the oxygen demand. Okay, to find out basically how much organics are there, right? So there are 3 different definitions. There is theoretical oxygen demand, the chemical oxygen demand, and the biochemical oxygen demand. So the theoretical oxygen demand is just based on stoichiometry. So everything gets converted into carbon dioxide and water. Okay, so for the sugar case, right, we have some calculation over there, right? So the chemical oxygen demand is using highly oxidizing agent, for example, the chromic acid, right, to oxidize the organics inside. But the limitation is that the COD basically is an overkill, right? It also will oxidize these highly oxidizing agent will also oxidize something that are not biodegradable. For example, the plastics, right? The bacteria will never eat plastics because they're so stable. So that's why people use the biochemical oxygen demand, which is a more realistic indicator of the water quality. So we said that under rare situations, these two will equal each other. Otherwise, they're not equal because the theoretical oxygen demand is so difficult to determine. There's no way we can have an accurate composition of the water. And then for the biochemical oxygen demand, it's always smaller than the theoretical and chemical oxygen demand, mainly because the BOD here represents the actual condition, right? So not all of the organics are getting converted to carbon dioxide, water, and at the same time, some of the organics are getting used as a part of the body for these bacteria, okay? So basically, the BOD represents how much oxygen is needed to break down the organics in the water. We further show that the BOD is a function of time, right? So normally, if people want to, let's say, determine what is a BOD in this water here, then they will take a sample of the water, put it into a bottle, right? and then bring it to the lab, and then to basically dilute it, first dilute it, and then add in the bacteria to see how much oxygen is getting consumed. Let's say they will do the measurement of the oxygen either after 3 days or 5 days or 7 days or longer, right? And based on the oxygen demand under certain days, for example, if you have the oxygen demand under 5 days, then you can use this equation here to calculate what is the ultimate ultimate BOD, right? So the ultimate oxygen demand for this sample of water here. So this is about the BOD and its change as a function of time and also the measurement. Okay, so just to give you a few examples, right? So again, this is the how the BOD change with time, right? So we said that the BOD is going to increase with time. At the same time, the organics concentration is decreasing with time exponentially. So just to give you a few examples of the BOD value. So if we take the sample of pristine river, right? So for example, go to the mountains, right? Directly take a sample of the water from a creek, right? Maybe the snow melt, then it's going to have a BOD of less than 1 milligram per liter, which is very small, right? If you think about the dissolved oxygen, again, as we said, 8 to 8.5 milligram per liter, right? So the BOD for this pristine water is basically nothing, right? It won't consume the oxygen in the water by a lot, right? That's why in this pristine river, you can see all different types of living species in there. So another example is the polluted river. So for polluted river, you are going to see the BOD of 2 to 8 milligram per liter. Okay, so this is already quite significant. So if you have the a relatively higher concentration of the BOD, right? And if it's approaching, let's say 8 milligram per liter, then it's going to drain all the dissolved oxygen in the river, right? So for example, if you take a water sample from the polluted river, right? Again, let's say we take a bottle and then bring it to the lab and then measure how the dissolved oxygen change with time, you're going to see a decrease, right? A decrease and then reach to a certain level. So basically, you're going to consume the oxygen in the water, right? And then about the sewage, for example, if you're talking about the treated sewage, this is what we have from the wastewater treatment plant, right? So normally that's in the range of around 20 milligram per liter. So already, if you have this treated sewage there, it does not support any living species inside, right? Because you don't have sufficient oxygen, because this value is higher than 8, right? Or 8 to 8.5 milligram per liter. So what about raw sewage? So you see that the raw sewage in the United States, so basically the raw sewage is what you get from the wastewater, basically the inflow of the wastewater treatment facility, right? So that's heavily polluted. You can reach to a BOD of 200. And if you compare that to Europe, right? So in Europe, it has a BOD value of 600. So then we may wonder, why is it? Why does the water in Europe has higher BOD value, right? So it's actually not because of the water in Europe is more polluted. It's actually because people use more water in the United States. Okay, so the I think by standards, right? So for the toilet flushing, so the standard in the Europe is that you have to use less amount of water in the toilet. Okay, so it basically flush less amount of water. And then in the US, you have a higher standard, you have a lower standard. Basically, you can flush more water through the toilet. And also in general, people in Europe, people in the US consume more water through the irrigation or from, let's say, the typical bathing every day, right? Or swimming pool. So that's basically giving a lower raw sewage value. So basically from these values, you can see that the BOD, when we talk about that, you can treat it as a pollutant, right? Although there isn't such a pollutant that's called oxygen demand. So if you go back to the name, right, this is oxygen demand. So it's different from, let's say, the heavy metals, for example, arsenic or mercury, right? There is a real thing, but for the oxygen demand, there isn't such a thing. There isn't such a chemical called oxygen demand. So basically, it's kind of like an analogy or kind of like an indicator of certain pollutants that are organic, that are biodegradable, right? So you can treat the BOD as a pollutant, right? It is equivalent to the biodegradable organic concentration, okay? So as we said, it's an indicator of the water quality. And actually, there is a federal regulation for the wastewater treatment facility, okay? So wastewater treatment plant. This is for abbreviation, wastewater treatment plant. So for their effluent, their BOD5 has to be lower than 30 milligram per liter, okay? So basically, if the BOD5 for the effluent of the wastewater treatment plant is higher than this value, then the plant has to be under either there will be a fine or there has to be some processes to get rid of this problem, okay? So this is about the BOD, and you can see that right now here we're mainly focusing on the carbonaceous species, right, that contains carbon. But actually for the organics in our environment, there's also species that's containing nitrogen, okay? For example, the protein, the amino acids, right, they contain nitrogen, and nitrogen species can also get oxidized, right? So previously we were just talking about the hydrocarbons, but that was under the assumption that only carbon will get oxidized. And actually the protein and other species, organic species might contain nitrogen, and they can also get oxidized, right? So they're going through this process. So the ammonium ion can react with oxygen and then form nitrate ions, water, and hydrogen ions. So because of that, when we talk about the BOD, then we have to separate them to the carbonaceous BOD, which is a CBOD, or the nitrogenous BOD, the NBOD. Okay, so the thing is that people will focus on the CBOD most of the time because the CBOD is easier for the bacteria to consume. So it's just like human, right? So or any other animals. So it's always easier to decompose sugar compared to the protein, right? So if you think about the sugar, right, for starch, they already get decomposed in our mouth, and then they can get digested. They can get picked up by the human body in the stomach, right? But for the protein, they have to get ingested or absorbed further down in our digestive system. It's the same for all the other bacteria too. So they will consume the CBOD first, and then is the NBOD, okay? In terms of calculating the NBOD, we can just use this equation here. So it's more like a theoretical calculation, right? So if you see from this equation here, this is already balanced. You have one number of the ammonium ion. It's going to react with two number of the oxygen molecules, right? So if you check the number of the atoms, right? So on the left-hand side, you have one nitrogen, right-hand side, one nitrogen, right? Left-hand side, you have 4 oxygen, right-hand side, you have 3 plus 1, that's 4 as well. And then left-hand side, you have 4 hydrogen. Here you have 4 hydrogen, right? This is already balanced. So basically, then we can calculate the NBOD just based on the stoichiometry, right? So here you can see that basically, if you have 1 mole of the ammonium ion, then it's going to react with 2 mole of the oxygen molecules, right? And further, for 1 mole of the ammonium ion, it has a molecular weight of 14 plus 4, right? And that's basically 18 grams, right? And then for 2 moles of the oxygen, you have 2 multiplied by 32. That's 32. Basically, you have 64 grams. Okay, so then you can see that basically for the NBOD, then you can just take the ratio between the oxygen, grams of the oxygen used divided by the grams of the nitrogen used, right? That's 2 multiplied by 32, that's 64. And then in the denominator, you have 14. So basically the NBOD is just 4.57 grams of oxygen per gram of nitrogen, right? So this is the oxygen demand that's brought by this 1 gram of nitrogen in the wastewater. Okay. So then if you further look at the BOD as a function of time, so we showed earlier that for carbonaceous BOD, right, for CBOD, it's changing as a function of time, right? So eventually it's reaching the ultimate BOD, that's L0, right? But initially it has a value of 0. Right now, if you consider the NBOD, then you have to add the oxygen demand furthermore, right? So if you look at the untreated sewage, again, this is the inflow into the wastewater treatment facility, right? So if you do the measurement of the BOD, right? So on the x-axis, this is time, y-axis, this is BOD. So you're still going to see this increase, but then as we said, the bacteria prefer carbonaceous BOD, right? Only when they don't have carbon, right? When they don't have sugar anymore, then they're going to consume these nitrogenous species or these protein in there. So this is going to further add the BOD into the water. This is NBOD, right? And then if you compare that against the treated sewage, so one thing in the wastewater treatment facility, let's say we mentioned that to treat the organics, we actually introduce bacteria in a system called the aeration tank. So what happened is that in that tank there, for our inflow of the wastewater, right, we have the outflow. At the same time, we raise those bacteria inside and we produce or provide the oxygen or air inside, right? This is called the aeration tank. So basically for the bacteria that we put into this tank, they cannot consume the nitrogenous species. So we don't have those bacteria in these aeration tanks. So that's why if you look at their BOD for the treated sewage, okay, again, you can see this increase of the carbonaceous BOD, but quickly these carbonaceous species got consumed. And then in the natural system, right, they can start to provide this NBOD. So basically the NBOD amount is the same if you compare the treated sewage and untreated sewage. And this is mainly because in the wastewater treatment facility, we don't have those bacteria treating the nitrogen species. But still we have done a lot by reducing the carbonaceous BOD. Okay, you see now the carbonaceous BOD is just this amount. But for the untreated sewage, you have much more carbonaceous BOD. Okay, so this is how the CBOD and NBOD gets to interact into the in our natural water systems. Any questions right now? Everything good? So how is the audio? Can you hear me clearly? Anyone?
Yeah, it's good.
It's good? Okay, thanks. So now let's talk a little bit about the application for the BOD. Okay, so as we mentioned, even for the wastewater treatment facility, there's no way we can reduce the BOD all the way down to, let's say, below 10, right? If you look at the example we gave earlier, right, for the treated sewage, it still has a BOD of 20 milligram per liter. Okay, so is that sufficient? Right. So, or do we need to do more work to reduce that further down to, let's say, below 10 or below 5? So to understand that problem, we have to evaluate how our natural water system can handle these pollution species. Okay, so for example, here, this is showing you a river, right? So as we introduced earlier in the introduction class, many of the civilizations are built nearby rivers, right? So the river provides you the drinking water and at the same time provides a way for transportation. So it's the same in the United States. Like the Mississippi River is our major river, right? There are so many cities along that river. And also, people will need to, let's say, on the one hand, we need to bring the drinking water from the river, but at the same time, we need to dump our wastewater into the river, okay? So for example, we're trying to set up a wastewater treatment facility nearby this river, and we're basically pumping in wastewater from here. Let's name this location as 0. Okay, this is point 0. Okay, so at the same time, we want to monitor the water quality further downstream of the river. So we can do measurement at 1, 2, 3, 4, 5. And then let's also do the measurement upstream of the river, let's say 0 prime. Okay. So at this location, basically we're adding in a pipe that's just pumping in the treated sewage, right? So that contains organics inside. Now let's just look at 2 indicators or 2 factors about the water quality. So one is the BOD, and the other is the dissolved oxygen. Okay, so basically this is the oxygen concentration in water. Okay, so if we compare the location, BOD and DO. So if we compare the location of 0 prime and 0, which location is going to have a higher BOD? Because it's 0 prime and 0, these 2 locations. So which location is going to have a higher BOD? It's going to be 0, right? So basically at 0 point, we're mixing these, at 0 point, we're mixing these treated sewage into the river water, right? So basically here, the BOD is going to be higher. But also at the 0 point, the dissolved oxygen is going to be lower, right? This is mainly because the dissolved oxygen at 0 prime, this is unpolluted water, right? This is relatively cleaner water. So you have more oxygen in there. But once you mix these treated sewage, you're going to have a lower dissolved oxygen concentration, okay? So what about the location 1? So 1 is downstream of this river here, okay? So what's going to happen to the BOD? Or let's say, let's start with the DO. What's going to happen to the DO? Is the DO going to decrease or increase? So the DO is going to decrease, right? Because you're consuming those organics. Right? So organics concentration becomes lower. Basically, the bacteria in the river are eating up those organics, right? You're lowering the dissolved oxygen in there. But at the same time, we should notice is that for the river, it's always in contact with oxygen, right? So the oxygen, although it's being consumed in the river, but at the same time, the oxygen in the air is adding back into the river, right? So eventually, let's say when we measure the dissolved oxygen at 0.5, it's going to have a higher dissolved oxygen concentration, right? Let's say 2, 3, 4, 5, until 5, right? So the dissolved oxygen concentration is going to be higher at 5, mainly because our environment, our atmosphere is adding in this oxygen back into the river, okay? So just based on this trend here, or this change of the dissolved oxygen concentration, you can imagine how the DO change as a function of time, right? So if you plot it as a function of time, or as a function of the sampling location, right, dissolved oxygen, let's say this is our point 0, right? And you have 1, 2, 3, 4, 5. You're going to see the dissolved oxygen concentration first decrease, okay, compared to what you have from the river. Okay, this is 0 prime. You have, so before you put in the sewage, right, you can have a higher dissolved oxygen concentration. Immediately after mixing, you have a lower dissolved oxygen concentration, and then it starts to decrease, right? So the decrease is because there is BOD, there is organics in the water, okay? But eventually, you're having oxygen adding back into the river water. So actually, the dissolved oxygen concentration is going to increase back. Okay. So this is what people call the dissolved oxygen, or the DO Sag curve. Okay, so basically, the dissolved oxygen is going to show you a sag, show you a decrease and then increase. Okay, so here I'm having I would say a better schematic diagram, right? So if you look at the dissolved oxygen, the DO, right? So immediately after the mixing, you're going to have a decrease of the dissolved oxygen, right? This is creating a DO or the oxygen sag, right? At a certain point, it's going to stop decreasing, mainly because we're adding the oxygen back into the water, right? From the atmosphere, right? And then it starts to increase, and eventually it gets back to the clean water. So this is going to put an impact onto the living species in the water too, because if you think about the clean environment, right? So basically, in the location that's upstream of this wastewater treatment facility or upstream of this outlet, right? So it has a relatively higher DO, higher oxygen concentration. So that's why you can have these higher levels of living species, right? Like fishes, right? So different types of fish. You have the trout, perch, bass, or some bacteria inside too, right? But once you have this outflow, this sewage that has a higher BOD, right? And then the type of the fish is going to change. Now you just have carp, which can live in these polluted water, but also some, let's say, insects in there. And further, as the dissolved oxygen concentration further decrease, then there won't be any fish inside anymore. So basically, the higher level of living species will become diminished, right? And now what you have is just going to be some insects or some bacteria inside. And then there's the recovery of the oxygen concentration, right? Because our atmosphere is pumping in water, pumping in oxygen into the water, right? Now you have the carp back. And then when you get to the, let's say the higher DO concentration region again, right? Then you have these more diverse species of fish in the river, right? You can have these trout, perch, bass in there again. So people actually name these different regions with different terms, right? For example, you have the clean zone. That's the upstream or very downstream of this pollution source. You have the decomposition zone. Decomposition zone is the location where the organics are getting consumed, right? You have the septic zone, which is the very polluted zone. This is an area, this is a section that you have very low concentration of the DO. You have the recovery zone where the oxygen concentration is getting back because the air or the oxygen in the air is adding back into the water, right? And then you finally have the clean zone. Okay. Any questions until here? Are you good? So if you're reluctant to turn on your mic, you can also type in the chat, okay? Any questions you can put in the chat too. So later on, so far so good? Okay.
Yep, it's good.
It's good. All right. So then if you further look at the processes that's influencing or creating this DO Sag curve, right? There are basically just two processes. So one process is the deoxygenation process. That's the process that's removing the organics, right? Consuming the organics requires oxygen, right? So this is a deoxygenation. So for this deoxygenation process, its rate is going to be dependent on the deoxygenation rate constant and also the concentration of the organics, right? Let's say this is the concentration of organics. Okay, and there's also the process that's pumping in the oxygen back into the river. That's the reaeration process, right? It's this process here. So the reaeration process is also dependent on a factor that's called the Kr here. So this is the reaeration rate constant, but also is proportional to the to the existing, or it's related to the existing oxygen concentration, okay? So it's actually proportional to the oxygen deficit. So let's think of two extremes. Let's look at this location here and this location here. So which location is going to have a higher reaeration rate? Okay, so basically, let's say A and B here. So if you consider the rate of the oxygen getting pumped back into the river, so the rate of the reaeration is going to be higher at A compared to B, right? That's mainly because A here, you have much lower oxygen concentration, basically needs more oxygen, right? There's more room for the oxygen to get replenished back into the river, right? As opposed to B, right? At B, the oxygen concentration is already pretty high, right? So the oxygen is going to be more difficult for the oxygen to get back. So basically, this reaeration rate is proportional to the oxygen deficit. So basically, how far this oxygen concentration is compared to the saturation level. Okay, so it's dependent on this level here. Okay, so the oxygen deficit can be calculated by the saturation dissolved oxygen concentration minus the actual dissolved oxygen concentration. As we said, the saturation level is just 8 or 8 to 8.5 milligram per liter, right? Let's say if we choose 8 here, right, 8 milligram per liter. If you measure it here, this is 2 milligram per liter. If you have 2 milligram per liter, and then the oxygen deficit, this D at this A location, is just 8 minus 2, which is 6 milligram per liter. Okay, so this is the oxygen deficit. All right, so now if you look at this DO Sag curve in a more mathematical way, right? So if plot it out, it's going to look like this. So the reason why people are interested in this DO Sag curve is we want to evaluate the impact of certain pollution source. For example, if you're trying to construct a wastewater treatment facility, right? How is that construction, or how is that outflow is going to impact the river water quality? Or if we're, let's say, accidentally spilled some contaminants into the river, right? How is that going to affect the river, the water quality along the river? And what is that impact as you further go downstream of the river? Okay, so that's why people want to solve this curve, solve this this problem analytically, because only with the mathematical equation we can better understand or do these engineering calculations, right? To find out the impact of certain pollution. So this is the mathematical curve, right? And then we need to find out the analytical solution for this problem. Okay, so now if we try to build up a differential equation for this oxygen deficit, okay, let's say we try to build up dd dt. Basically, the change of the deficit, as we said, is dependent on two terms. You have the deoxygenation, and then you have the reaeration. Okay, so assuming that both of these terms are positive, what is going to be the sign in front of these two terms? Okay, are they going to be positive or are they going to be negative? So first, let's look at the deoxygenation. All right, is it going to be positive or negative? So,
I'm sorry, Professor, could you repeat that?
Okay, so let's look at the change of the oxygen deficit. Okay, so let's try to build up a differential equation for the oxygen deficit, this D here. So we said that the oxygen deficit or the dissolved oxygen concentration is just affected by two processes. That's the deoxygenation, which is the consumption of the oxygen due to the organics getting decomposed, and also the reaeration, which is adding the oxygen back into the river. Okay, now if we try to evaluate the influence of these two terms, is the deoxygenation going to increase, basically have a positive impact onto the oxygen deficit or a negative impact onto the deficit?
So is it because like the slope is increasing, we have a positive?
It should be positive, but actually the reason is, let's think of extremes, right? If you have more deoxygenation, if you have faster deoxygenation, are you going to have a higher deficit or lower deficit?
If you have more deoxygenation,
Uh,
then I guess you would have a higher deficit.
yes, that's right. Okay, so that's why this term should be positive. Okay, and then
Okay.
about the reaeration, if you have a faster reaeration, then do you have higher deficit or lower deficit? So you're going to have a lower deficit, right? So the faster the reaeration, right? It means that more air is more oxygen is getting pumped into the river, right? Then you're going to have a smaller deficit. Okay, so that's why the term in front of the reaeration should be negative. Okay, so if we try to build up a differential equation, right, it's dependent on these two terms, right? The deoxygenation and the reaeration, right? So the symbol in front of the deoxygenation should be positive, and the symbol in front of the reaeration should be negative. And now let's just look at the expression for these two terms. We said that the deoxygenation depends on the consumption of the organics, right? So this rate is dependent on the decomposition rate and the organics concentration, right? So that's just KD multiplied by L, right? And then the reaeration rate is dependent on the reaeration rate constant, right? This Kr here. And also the oxygen deficit, right? This D here. Okay, so this is how we can build up this differential equation. So it's going to look like this. All right, any questions until now? So far, so good?
Yes.
Okay. Yeah. So this is our differential equation. Well, if you are not clear, you can also send me a private chat. Okay, so I can go over that. All right. So this is our differential equation. So now let's try to solve that, because as we know, our goal is to find a mathematical equation, mathematical expression for this DO Sag curve, right? So further, right? So if you look at these terms here, right? The D here, this is the oxygen deficit. It's calculated by the saturation dissolved oxygen concentration minus the actual dissolved oxygen concentration, right? The T here is time. The KD is the decomposition rate constant, or the deoxygenation rate constant, right? L here is the organics concentration, organics remaining in the river water, right? And then you have the Kr, this is the reaeration rate constant, and D, again, this is the oxygen deficit, right? So we're trying to find out what's the expression for D. Okay. So if we know that the KD and Kr are already constants, then we just need to find out what is L. So, so the L, which is organics in the river, right? That's actually L0 exponential minus KT, because for the organics, their concentration is going to decrease exponentially, right? If you recall at the beginning, we showed this curve here, right? So the organics concentration is decreasing exponentially. Okay, so basically we also have an expression for the L term here. So now it seems that the only unknown is just the D. So D is the oxygen deficit, right? So you can basically try to find out what is analytical expression. I think you probably have gone through this in your calculus class, but if you're interested, we can derive this together during our office hour. Okay, so now for this differential equation, if you want to find out its final solution, on the one hand, you need to find the analytical expression, but at the same time, you need to know what is the initial condition. Okay, so basically here, you need to know what is the oxygen deficit at time equals 0. So what is the oxygen deficit, right? So again, if you go back to the, let's say the definition for the oxygen deficit, right? This is DOS minus DO. And more specifically, let's name this time equals 0 term. Basically time equals 0, this is the mixing point. Okay, so let's put this subscript A here to represent this initial time. Okay, let's call this DA, D sub A, right, equals DOS minus DO sub A. Right. So the DOS, this is a saturation, dissolved oxygen concentration. This is a constant, right? It's between 8 to 8.5 under normal condition, right? And then for the dissolved oxygen concentration, this is just the problem of mixing, right? So if you remember, when we introduced the physical mixing of two streams, right? If you can recall the problem of mixing two streams that have salt inside, right? So about the snow melt, we have one stream, the sewer water has salt, and then the other stream has clean water, and then there's a physical mixing, right? It's the same for the oxygen, right? The dissolved oxygen concentration in the wastewater is going to mix with the dissolved oxygen that's in the river water, right? And then you can find out what is the dissolved oxygen in the mixture, right? So the DO in the mixture is just going to be the flow rate of the wastewater multiplied by the dissolved oxygen in the wastewater plus QR multiplied by DOR divided by QW plus QR. Okay, so this is the dissolved oxygen concentration after mixing. Okay, and this is at time equals 0. Okay, so it's the same for the organics concentration. So you remember here for the organics, right? We said that it's dependent on the initial condition, right? Basically, it's dependent on the initial organics concentration at the mixing point, LA, right? So LA can be calculated by QW multiplied by LW plus QR multiplied by LR divided by QW plus QR. Okay, so this is how we can find out the initial condition. Okay, so you can find out the dissolved oxygen concentration right after mixing, and then the organics concentration right after mixing. And then if you recall, for this equation here, we need to find out the initial condition for D, which is the oxygen deficit, right? So the oxygen deficit is just the saturation condition minus the DO right after mixing. Okay, so in this way, you have the initial condition, you have the differential equation, you can solve that, right? And this is our final solution. Okay, so you don't have to memorize this. You can just put this on your cheat sheet, or when you do the calculations, or you can directly use this equation when you work on the homework problems. So basically, this is the oxygen deficit at any time downstream of a mixing point. Okay, so let's say if you plot the DO Sag curve, right? So the oxygen deficit is basically the distance from this point to the saturation point. Right, this is DOS, right? The oxygen deficit is just this distance here. And this equation here is the expression for this oxygen deficit. Okay, so you can see that this equation is dependent on the deoxygenation rate, right? The reaeration rate, the organics concentration, right, after mixing, right? And then the time here. Okay. So basically with this equation, you can evaluate what is the impact of a pollution, let's say a source, single source pollution on the river water quality, right, at any time. Okay, so this is the equation here. Any questions until now? Are we good? Concerned? Confused?
I have a quick question.
Mhm.
What does the K, so Kr is the reaeration constant. What does Kd represent?
Kd represents the decomposition or the deoxygenation rate.
Oh, okay.
So it's kind of like the decomposition rate for the organics. Okay. So one thing that I didn't mention is that basically for the deoxygenation rate, it's just depends on the bacteria, right? Depends on what type of bacteria is in the environment. But for this reaeration rate, it really depends on the process, or it really depends on the river. Okay. So there's a equation to determine that, which is shown in here. Okay. So the Kr is dependent on the river velocity and the depths of the river. Okay, so you can think of it, let's say we have a river and then it has a very fast flowing speed. If it has a fast flowing speed, it means that the river is going to be more turbulent, right? If you have more turbulent river, then the reaeration process is going to be faster because you generate more waves, more bubbles, right? And there's a better contact between the river and the air, right? So the oxygen can get pumped back more quickly. And then it's also dependent on the depths. If you have a very shallow river, right, then it's easier for the oxygen to get in. If you have a very deep river, then it's more difficult to let the oxygen get back into the river, right? So that's why it's in the denominator, right? So the velocity is the numerator. So there's a positive correlation between the reoxygenation rate, reaeration rate, and the velocity, and a negative correlation between the reaeration rate and the depths. Okay, so this is a simple equation to determine these values. Okay. So let's get back to this equation here. So basically, I would say with this equation, then we can determine the impact of certain pollution sources, right? So how do we do that? So here I have a example problem. Okay, so this is also an example problem on your textbook. So this is trying to evaluate how a wastewater treatment plant is going to influence the water quality in a river. Okay, so we can spend maybe 1 or 2 minutes to just look at this problem. Okay, so let's start to look at this. So it's describing a city, right? The city has around 200,000 people, which is, I would say, a small city, right? Compared to Miami-Dade, we have more than 2 million people, right? So I would say this is talking about a smaller area and then also a smaller wastewater treatment plant. So it says that it's disposing treated sewage, basically the outflow of a wastewater treatment plant at a flow rate of 1.05 meter cube per second. Okay, it has a BOD, the ultimate BOD of 28 milligram per liter, right? So we mentioned earlier in the class that federal regulation puts a limit of 30 milligram per liter. Okay, so you can see this value is very close to that. Basically, but it's still lower than that. It means that the treatment facility is doing a pretty good job, right? And then this sewage or the waste also has 1.8 milligram per liter of dissolved oxygen, right, in this waste sewage. And then it says that upstream of this outfall, basically this a mixing point, the river has a flow rate of 7.08 meter cube per second. Right, this is a clean water and has a velocity of 0.37 meter per second. And also at this point, basically in the clean water, it has a BOD of 3.6, and then the dissolved oxygen of 7.6. So there are quite many numbers here. What we can do is we can try to draw a schematic diagram, right, to just show this physical mixing process. So we have this waste, right, basically coming from the wastewater treatment plant. We have this clean water, or this river water. And then there's mixing, right? And then we have this further downstream, right? So the DO Sag curve, right, the dissolved oxygen is going to decrease and then further get back, right? So basically, from this condition here, we can try to write out the different values. Okay, so you have the wastewater, right? Wastewater condition, it's giving you the flow rate. So Q waste is 1.05 meter cubed per second. And then the BOD waste is 28 milligram per liter. And then the dissolved oxygen concentration, DO waste, is 1.8 milligram per liter. Then at the same time, it's giving you the properties of the river. Okay, so it's giving you the flow rate, right? This 7.08, this is the river flow rate. So you have QR equals 7.08 meter cubed per second, right? And then it gives you the BOD of the river water. So BOD river, this is 3.6 milligram per liter. And then the dissolved oxygen concentration is 7.6 milligram per liter. Okay, so these are the conditions, right? And so then it's further giving you some constants. For example, the saturation value of the DO is 8.5 milligram per liter, right? So basically it's giving you that DOS, this saturation value is 8.5 milligram per liter. And then you have the deoxygenation coefficient, KD is 0.61 per day. And then you have KR 0.76 per day. Okay, so these are all the conditions. Okay, and further you have this velocity of the river. Okay, velocity 0.37 meter per second. So this is how fast the river flows. Okay, so now let's look at the problem. So the first one is asking, what is the oxygen deficit and BOD just downstream of the water of the outfall? Okay, so basically this is just after mixing. Okay, so it's asking for what is the oxygen deficit at this mixing point? As we said, we're using the subscript of A and then the BOD of A point, right? So to do that, to calculate this mixing point, then we have these two equations, right? This is the property at the mixing point, right? So you have the dA equals the equals this term here, right? So you have the DOS. This is the saturation. These are oxygen concentration. That's 8.5, right? And then you have the Q waste. This is the wastewater flow rate. The DO waste is here, right? That's 1.8. The QR, this is the river flow rate, and DOR, this is a river DO, right? And further, you divide that by the mixture flow rate to find out what is the oxygen deficit at this point. So you can also find out the BOD, which is the organics concentration, by using the similar equation here, right? By using this equation. So basically, if you plug in these values, you'll be able to find out that for the dA, you have a value of 1.6 milligram per liter. And then for the LA, or the BOD right after mixing, right, you have a value of 6.75 milligram per liter. Okay. So now if you look at the problem 2, right, so it's asking what is the DO? What is
Professor?
the DO? Yes.
I'm sorry. So BOD and L we're treating them as the same thing?
We're treating them as the same, right?
Okay.
So L, yeah. So basically here, what happens is that the organics, we're saying that the BOD is equivalent to the organics concentration that's consuming the oxygen, right? So yeah, we can treat them the same. Yeah, that's a good question. So basically here, we're treating them the same thing.
Also, the DOS in this
Mhm.
formula for DA, that would be the upstream dissolved oxygen content, right?
The DOS is the saturation. It's the saturation of the oxygen, right?
Okay.
Because the deficit, let's say, if we go back here.
So is that always just like 8 milligrams per liter or whatever we discussed?
Yes.
Okay.
This is always, let's say for this problem, it's giving you 8.5, right? But really depends on the temperature. You're talking about, let's say, hotter environments, let's say 25 Celsius, this becomes 8, right? But the deficit is how far the DO is from the saturation, right? So that's why you take the difference between the saturation and the DO in the water.
And then the DOW and DOR, they correspond with.
Yeah, that indicates the waste, and R indicates the river.
Okay, makes sense.
Yeah. Okay. Any other questions? Yeah, you can also type in your question if you're having trouble with your microphone or anything. Okay. So this is how we can solve problem 1. And then how do we solve problem 2, right? So it's asking what is the DO 16 kilometer downstream? Okay. So if you look at this equation here, so basically this equation is a function of time, right? But this is asking us a distance, or asking us a location. So how do we do this conversion here? Or how do we relate this location to time?
With the velocity?
Yes, with the velocity, right? So the river has a velocity, all right? So if you calculate this time, right? The time needed for this river water to flow to this location 16 kilometer downstream, right? You can do 16 kilometer, that's 16 multiplied by 10 to the 3rd meters, and then divide that by 0.37 meter per second, right? And further convert it into days. You can see that this is exactly 0.5 days. Okay, so the river is going to take half a day to flow this, flow by this 16 kilometer. Okay, So now you can plug in this 0.5 into the time here. And you have everything else. You have the KD, the oxygenation rate, the organic concentration rate, that's the right after the mixing, right? You have the KR, right? This is the reaeration rate. Again, this is KD. So time is here. The DA is the oxygen deficit at the mixing point, right? So you can find out that the basically, let me see. So basically you can find out what is the oxygen deficit, right, at this 16 kilometers downstream. And then to find further calculate the dissolved oxygen concentration, then the dissolved oxygen is the DOS minus the oxygen deficit. Right. So I don't have the exact answers here, but you can refer to this example in your textbook to find out what is the exact value. Okay. So what I'm trying to show in this problem is that if we have this equation here, if we have this set of analytical equation here, we can evaluate the impact of any point sources. It can be a wastewater treatment facility. It can be a, let's say, a coal-fired power plant, right? It can be, let's say, some unintentional contamination. For example, if a truck that's carrying some chemicals having a spillover, right, into the river, right, we can evaluate how far this contaminant is going to put an impact onto the river, right, at any location, basically by using this analytical expression here, right? So this is how we can evaluate the river water quality by using this concept of the BOD, or the dissolved oxygen, or the DO, or the oxygen deficit. Okay. Any questions until now? Are we good?
I have a question.
Mm-hmm.
So these set of equations are specifically used when we have like water that's flowing. So
Yes.
that's why it's
So this
particularly
is,
useful for like rivers or streams or canals or whatever.
yes, yes. So this is just
Okay.
for river water quality. So if you have a lake, if you have a pond, then I would say it's more dependent on how fast the mixing is, right? If you can assume it's a CSTR, right, then you can evaluate how the time is going to put an impact onto the system, right? Okay. So actually, since we talk about CSTR, so for this river here, we're actually treating that as a PFR, right, as a plug flow. So there's no mixing across the river, but there's so there's no mixing along the river, but there's mixing across the river, right? Okay. So again, basically we have this analytical expression here. Now we can look back on this DO Sag curve, right? So for the Sag curve, we have the decrease of the oxygen and then the oxygen increase back, right? And I would say that people are going to be very interested in this lowest point, this point that has the lowest dissolved oxygen concentration or the highest oxygen deficit, right? Because we want to make sure that this lowest point has sufficient oxygen so that some bacteria can still live in there, right? One thing we definitely want to avoid is to have this curve decrease all the way down to zero, okay? So if it's decreasing down to zero, then that's going to take a longer time for the oxygen to get replenished back, right, into the system, right? You can think that if we have any amount of oxygen after it reaches zero, if we have any amount, then it's going to react with the organics in the river, right? So the oxygen is going to maintain at the lowest point for, or at zero for a very long time before it can recover back, right? So that's why we're quite interested in this lowest point, right? And with this analytical expression, we can also find out where this lowest point is, right? Because this is point that's having a either maximum or the minimum, right? To find out the minimum point, what we can do is we can take the derivative of this term, right? So basically just take the we can just calculate the d dt, right? So let me see. So we can calculate the d dt dt, and then set this to be 0. Okay, so if you set this term to be 0, then you have, or you can find out where this critical point is. You have TC over here, and then DC over here. This is a critical oxygen deficit, right? So we want to make sure that the oxygen deficit is definitely below or smaller than the DOS, so that we can still have sufficient dissolved oxygen at this critical point. Okay. Any questions? Good. Okay. So now let's have let's say a quick quiz here. I won't count your participation, but this is just to see if you guys know these concepts here. I think I need to first create it. So you can take a read at this question first. Okay, so what is the critical point? I just launched the quiz. Okay, let's give it maybe 1 minute. Yeah, well, no need to wait for 1 minute. Okay, so let me share the results. Right, so all of you got it right. Okay, so the critical point is going to be the point that has the lowest DO. All right, so next is about some common issues in terms of the water quality management, right? So we just introduced the theoretical dissolved oxygen concentration, but actually when we evaluate the water quality in rivers, we also need to consider other factors. For example, let's say if we want to make sure that the pollution source is not influencing the river water quality, we need to set up a minimum dissolved oxygen concentration, right? So this is the first bullet point here, right? So we need to set up a standard. Yeah, we need to set up standard, right? If we realize that the dissolved oxygen concentration is too low, then we need to talk to the pollution source, right? For example, the wastewater treatment facility to reduce the organics by the increased treatment, or we can also try increase the dissolved oxygen by aerating the wastewater. So one common thing we can do is to create, for example, more bend, right, in the wastewater channel so that it can have more or a longer residence time in these channels. So it has a longer time for oxygen to get back. Or we can also bubble air through the wastewater, so produce more oxygen into the water. And also when we evaluate the river water quality, if you recall on the equation, right, so there are factors of KD, KR, right? And then there's LA or the DA, right? So for these factors, they're also dependent on which environment we are evaluating them, right? So we can do the measurement during the summer or the winter, right? But if we really try to evaluate the worst case scenario, people will do the measurement during the summertime, okay? Because the summertime, the river water quality is most impacted by these organics. So the reason is that, during the summertime, you are going to have a much lower river flow because of evaporation. So if you think back on the let's say if you have a wide river, right? So during the summertime, because of evaporation, the flow rate will become much lower. If you have a lower flow rate, then the dilution of these organics will be lower. So basically, you're going to have more organics in the river. And also during the summertime, you're having a lower velocity, right? If you have a lower velocity, then the recharge rate or the reaeration rate is going to be lower. And also during the summertime, you have a higher temperature. So the higher temperature corresponds to a higher oxygen consumption. So if you draw the DO Sag curve, right, then your oxygen is going to consume at a faster rate, right? And then it's going to come back. As compared to winter time, then this deoxygenation rate is going to be lower. And then you have this more rapid increase of the dissolved oxygen, right? And then also at the higher temperature, you're having a lower saturation dissolved oxygen concentration. As we introduced, generally, if you have cooler water, right? If the water is cool, then the saturation concentration is higher, right? This is DOS. So the higher the temperature, the lower the saturation concentration. So all of these factors point that during the summertime, we're having the worst case scenario of the water quality for the river water quality, right? But during the winter time, the water quality is going to be better. Okay. So this is about the these measurement considerations, right? So there are also other factors affecting these DO. For example, if you have multiple discharge points, then the scenario will be more complicated, right? Or if you have non-point sources, for example, coming from the farmlands, right? And normally, if you have these scenarios, people will divide the river into different stages and then build up analytical solutions to further predict the water quality. And if you have aquatic plants, then we further need to think about how the oxygen is going to change with time. For example, during the under the sunlight, you're going to have higher oxygen concentration, but without sunlight, right? It consumes the oxygen, so that's going to have a problem. And when the aquatic plants die off, right? This is talking about the algae blooms. If they die, then they form organics, right? Then they're going to further reduce the water quality there, right? And let me see the final slides here. Okay, so this is the final slide about the river water quality. So this class we mainly discuss the basically analytical solutions for predicting the dissolved oxygen concentration, oxygen deficit. Okay, so you're also going to get some practice from your homework problems. So next class, we're going to finish on the lakes, estuaries, and oceans, and then we'll talk about the water treatment. Okay. Any questions until now? We good? Okay, so that's it. So I also share with you the recording of this class. So if you have any questions, you want to go through these contents again, you can do that. All right. Okay. Thank you, guys. Bye.
Thank you.
Thank you.
Bye.